Welcome to the AP Physics Workbook tutorial. This is Unit 8, Electric Charge and Electric Forces. This section is 8.b, the electric force. Here's the scenario. You can read the scenario to yourself. Part A asks us to draw the relative lengths of all vectors to reflect the relative magnitude of all the forces in these two situations. These are two of the same charges. We're going to see how these two charges react. If you take a look here, you would see that if they are the same forces, they will repel. So force 1, 2 is the force on 1 due to 2 is the same thing as the force on 2 due to 1. Notice that here these charges are the same strength. So they're going to repel at the same length. So I can write here that this will repel 1, 2, 3, and this can be the force, and this is the electric field. So you can draw F of E is pulling, goes to the left, and this one 1, 2, 3 as well, and this also goes to the right. And this is because these two charges are the same in magnitude, and they are the same in terms of they're both positive. So they are going to repel each other. Now you have this scenario. They have the same charge, so this is going to repel. But this time, this one is stronger because it is 5Q. Now we're going to draw the forces to reflect the electric field. Before we do part B, I would like to do part C first to show you the math for it. If you would like to see the equation, we are referring to Coulomb's law. Coulomb's law is the magnitude. Q times Q over R. That is Coulomb's law. Right? You can see it down here where I give you a little bit more information on Coulomb's law. The direction of the static electric forces one point charge exerts on another is always along the line joining those two charges. This depends on whether the charges are, in this case, the same, so they're going to repel each other. This gives you the magnitude. So let's use Coulomb's law. So the new force is going to be the initial force equal K Q1 Q2 over R squared, which is the distance between them. Right? Now, we saw that the right increased by 5Q. So the new one will increase by 5Q. So Q1, Q2 is going to be 5Q2 over R squared. Okay? Simplify. This is K. You could pull out the 5 here, so it can be 5K Q1 Q2 over R squared. K Q1 Q2 over R squared is just the original F. So the new force, when we multiply the magnitude of the charge by 5, it's going to be 5 times as much. So this says that the new force is 5 times as much. Okay? Please understand that this is a linear direct, it should be direct linear relationship. Okay. The charge has a linear direct relationship with the force. I should write that here. That might be very useful for you to memorize. Okay, the charge has a direct linear relationship with the electrical force. The electrical force. I don't like that word, but okay. The electric field, maybe. Right? Okay. There you go. So in this case, the original was 3, so it's going to be 5 times as much. So remember, this was 3 units. 3 units. Okay, but this time this is 5, so this has to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it has to be 15 units here. It has to be 5 times as much. FE. This one also has to be 15. So 15 units. And this is also FE. And again, the reason why it repels is because they are similar forces, charges. It says on the right to determine a position where a third point charge, negative Q2, negative 2Q can be placed so that the net electric force on them between those two charges will be 0, and explain. All right. To do this, this problem comes from this in the textbook. So if you would like to look at these notes, you should pause the video and read this. This should give you a clear explanation and show you the math for something like that. All right. Now I'm going to show you the solution for this problem. The solution for this is as follows. The third charge would have to be placed on the parallel line that connects the two charges so that it experiences no net force, since the force will be aligned but in opposite directions. 2. If you actually place that negative 2Q charge in the middle, there will still be a net force towards the 5Q. The reason why the negative 2Q will need to be near, or small r, next to the positive Q is because positive Q is weaker in magnitude than the 5Q. So the charge would be here, somewhere right here. Okay? This would be where that negative 2Q charge would be. And I explained it again right here. They have to be directly, along, has always, on another is always along the line joining the two charges. That's why it's aligned away these two charges. And this problem to the right should show you the calculation, right, to why this is correct. Okay? And there's an interesting note here that you should read as well. Next, the argumentation. Explain what is wrong with this statement in a few sentences. There's a lot that is wrong with her statement, okay? So I wrote it down here. There are 2, but everything that she got wrong can be explained in the textbook, okay? So the first 2 things. 1, the students assume that the positive direction is to the right, but the coordinate system can be defined in any way. We default to anything going up and to the right is positive, but that's not always the case. 2, Coulomb's law gives us actually the magnitude of the force, so there should be an absolute value sign around the product of those two charges. The two charges model states that opposite charges will attract while same charges repel. So her statement right here is all wrong. She says that Coulomb says that the force between charges is equal to that. The two charges are both negative and the force would be positive. That means it's to the right. So this is completely wrong. You do not know where it goes, and it will be positive. That is correct. That is correct. That's the electric field. So in the book, what you need to understand about Coulomb's law is right here. This is everything that you need to understand about Coulomb's law. You could read this to yourself, but the main points, exactly like what you can use in your explanation to the argumentation in part E. Coulomb's law, right here, gives us the magnitude of the electric force that either charges exert on each other. The direction of the electric force is always along the line joining those two charges. If those two charges have the same sign, the force on either charge is directly away from each other. They repel. If those two charges have the opposite sign, like plus and negative, they will directly point towards each other. Okay, when calculating with Coulomb's law, we usually use the magnitude, ignoring the sign of the charge. Or you can just do the absolute value. and determine the direction of the force after, which is separate, based on whether the force is attractive or repulsive. Remember, Coulomb's law gives you a magnitude, not a direction, gives you a magnitude. The direction comes from the two charge system that we use. All right. So there you go. That is everything that you need for 8B.